Hey everyone, welcome to this lecture series of digital signal processing. This is the first video in the lecture series, and in this video we will introduce ourselves to digital signal processing. Here is the outline of this video. First we will see what is meant by digital signal processing. Then we talk about signals and their classifications. Later we will see the block diagram of a DSP system, followed by the advantages, disadvantages and applications of a DSP system. So let's get started. What is digital signal processing? Digital signal processing is concerned with the representation of signals by sequence of numbers or symbols and the processing of these sequences. As you can see, there are three main points in this sentence: signals, representation of signals, and processing of these signals. So, what is a signal? A signal can be defined as a function that conveys information generally about the state or behavior of a physical system. For example, while I'm speaking, I'm generating audio signals using my vocal cord. For instance, when I say out the alphabet A, I'm generating an audio signal that conveys the information of alphabet A. Now mathematically, signals are represented as functions of one or more independent variables. If we take the same example of audio signals, the amplitude of my voice can be plotted as a function of time. That is, if we take time on the x-axis and on the y-axis if we plot the corresponding amplitude at each instance of time, we get a signal. Here, the independent variable is time t and the signal, which is my voice, is plotted as a function of time. If you see, this signal is defined continuously in time. Also, it has continuous amplitudes. So, this is an analog signal. Another form of signals are discrete signals. They are signals that are defined only at discrete units of time. To obtain discrete signals, all we have to do is sample the analog signals at discrete units of time. For instance, let's sample this analog signal. For that, first let us split the time axis into discrete units. That is, we mark the x-axis at equal distances. Then we obtain the amplitude of signal at these discrete times. Now, if we plot only these points, we get a discrete signal. Let me show that to you. So let me cut this discrete points and paste it over here. So this is a discrete signal. Okay, now many people often confuse analog signals with continuous time signals. Let me make this very clear for you. Analog signals and continuous time signals are not the same. Another common misconception is that discrete signals and digital signals are the same. Even the name of this course, digital signal processing, is based on that misconception. But understand that digital signals and discrete signals are not the same. So the true name of this course should be discrete signal processing, as we are only dealing with discrete signals throughout the course. But since universities around the world name it as digital signal processing, I am also following the same name. For those who are interested, I am explaining the difference between these four signals in another video, and the link to that video is available in the descriptions below. Okay, so far we learned what is a signal, how signals are represented, and how signals are classified into analog and discrete signals. Now let's learn what is signal processing. Signal processing involves analyzing, modifying, and synthesizing signals to pull or extract meaning out of it. Signal processing can be broadly classified into analog signal processing and digital signal processing. As you can guess, analog signal processing deals with transformation of analog signals, and the processing is done using electrical networks consisting of active and passive elements, that is, op-amps, resistors, capacitors, inductors, etc. On the other hand, digital signal processing deals with the processing of discrete signals. Here, the processing is done by general purpose computers or by digital circuits such as ASICs, FPGAs, or specialized DSP chips. Now let us understand the block diagram of a DSP system. There are mainly 5 blocks in the diagram. They are pre-filter, analog to digital converter or ADCs, DSPs or digital signal processors, DACs or digital to analog converters, and post-filter. This pre-filter is usually a low-pass filter and is used to filter out unwanted high-frequency components from the raw analog input signal. For example, if we are processing audio signals, we only need frequencies in the range of 20 Hz to 20 kHz, and this pre-filter will filter out any frequencies above 20 kHz as they can cause noise. Next, the ADC will convert analog signals to digital signals. Then these signals are fed to the DSP where it is analyzed and processed, and the synthesized output is fed to the DAC. The DAC converts digital signals back into analog signals. And finally, this post filter is used to filter out any unwanted high frequency components in the generated analog signal. Now, most often, we also provide an amplifier at the beginning and at the end. This is to amplify the incoming and outgoing signals. Now coming to the applications, we use digital signal processing in many areas. It is used to process speech and audio. This involves speech recognition and analysis, noise filtering, echo cancellation, etc. It is also used to process image and video. This involves compression, enhancement, reconstruction, and restoration of images and videos. It also involves face detection, like in the case of face unlock in phones. DSPs are also used in military and telecommunication applications. For example, sonar and navigation, radar tracking, modulation and demodulation, etc. Next application is in biomedical and healthcare sector. For example, analysis of ECGs, EEGs, and X-ray signals. Another application is consumer electronics. Most digital equipments in your home like smartphones, televisions, digital cameras, etc. have a DSP embedded in it to accelerate its performance. Now let's see the advantages of DSP. The main advantage of digital signal processing is its simplicity. That is, compared to analog signal processing, digital signal processing can perform complicated signal analysis with relative easiness without the use of complex circuits. Also, the processing can be easily modified with simple changes in software. That is, DSP systems are flexible. Also, with DSPs, we have access to many error detection and correction features. For example, parity generation and correction. Also, with DSP systems, data storage is easier. Since digital storage devices are becoming cheaper day by day, storage of data is much easier in digital forms. It is also easier to transport and recreate digital data with 100% fidelity. Another advantage is low cost. With advancements in VLSI technology, the cost of DSPs have come down by many folds than their analog counterparts. Now coming to the disadvantages of DSP systems, DSPs are made out of a lot of transistors, and these transistors together consume a lot more power than analog signal processors. Another problem is the higher learning curve required for the operation of DSP systems. Each DSP has different hardware architecture and software instructions. Due to this, highly skilled engineers are needed to program the device, and proper training on DSP is required for programming for various applications. Okay, now let's summarize what all we learned in this lecture. First, we defined a signal, and we learned that signals are primarily classified into analog signals and discrete signals. Then we learned about signal processing, which is analyzing, modifying, and synthesizing of signals. Then we saw the block diagram of DSP systems, followed by the applications, advantages, and disadvantages of DSP systems. I hope all the concepts that were taught in this lecture are clear to all of you.